the recording. Okay, so ready for the last two talks of our session. And it's a pleasure to introduce Santiago Saglietti from Universidad Católica de Chile, who's going to talk to us about heavy-tailed ballistic deposition with sticking.
Okay, so thanks, Daniel, for the introduction. It's a pleasure being here. So I want to thank the organizers for inviting me. And okay, so today I'm going to be speaking about some joint work with Francis Gomez from Paris University and Joseba Dalmau from NYU Shanghai, which, as Daniel said, is about heavy-tailed ballistic deposition. So something like what you see here in the animation. So before I explain what this heavy-tailed ballistic deposition is, I think I should first start with the standard ballistic deposition and then explain how we get these heavy-tailed variants. So, well, I should say version, not variant, maybe. Okay, so so the standard or the original model of ballistic deposition with p-sticking, let's say, is a model for surface growth or for the evolution of an interface, if you want, in which we have a cluster of blocks like the ones you can see here in this picture, or the ones that you saw in the animation above, which is going to grow with time by the addition of new blocks, which are going to attach to this cluster, okay? And okay, the way that this model is going to work is the following. So imagine that we have such a cluster of blocks, which is growing above the real line, okay? And the evolution of this cluster, it evolves with time as follows. So for each site x on the integers, I'm gonna have one by one blocks, like the one here on the figure, falling down vertically at random with rate 1, okay? So imagine that for each x, I have a Poisson process with rate 1, and every time the Poisson process, the clock from the Poisson process rings, then a block falls from the sky right above x, okay? And this is going to happen independently for each of the x's in the integers, okay? So all these Poisson processes are going to be independent, okay? And then whenever a block falls above some given site x, this block has two possibilities. So what I want you to imagine is that each block carries its own coin, which is going to be heads with probability p and tails with probability 1 minus p, where p is some fixed parameter, which explains the term p-sticking here, okay? And so whenever it falls down, the block is going to flip the coin, and depending on the outcome of the coin, it's going to decide to stick to the growing cluster of blocks in one of two ways, okay? So with probability p, if the coin is heads, it's going to decide to stick to the first point of contact, okay? So for example, if you have the situation or a situation like this, where we have a block falling over this side x, okay? Then the first point of contact would be this corner right here, okay? Which belongs to this block right here on a column which is a neighboring column to the one on which the green block is falling, okay? So for example, if the block, for example, is falling on this column, okay, then the first point of contact is just going to be the last block on this column below, or sitting above this site right here, okay? So depending on whether this column is actually higher or lower than the neighboring columns, okay, we may have that this block, whenever the coin is heads, is going to stick to either this column or one of the neighboring ones, okay? Just like what you see here in the picture. And then with probability 1 minus p, if the coin is tails, then the block will disregard any of the neighboring columns and will just fall straight down and attach to the cluster on top of the last block in the column of blocks sitting above X. Okay. So is this clear? Do you have any questions so far? Clear? Okay.
So Santiago, the sticking is really in the corner, or
it's really in the corner. So, no, it's really in the corner. So I think the usual ballistic deposition model is sticking to the side. So it's like the first side of contact is something like this. Okay.
Yes.
I don't think it really matters much for what I'm going to discuss today. But since I'm going to be working with blocks with random heights, it's more convenient to, well, you will see later, it's more convenient to make it stick at the first point of contact. Okay.
Okay.
Okay. Okay, perfect. Because so it may happen that this block doesn't have the same height as this block in the next model. So how do you stick them together? So you have to make a choice somehow. So. Okay, fine. So here I brought two animations, which I shamelessly stole from someone else called Tom. And okay, you can see that the traditional ballistic deposition model is the model I just described for P equals 1, which is just the model in which all blocks stick to the first point of contact. Actually, in this animation, the blocks are sticking to the first edge of contact, just like Daniel said, but okay, just picture that they're not. And for P equals 0, we actually get a different model, which is usually called random deposition. And you can see that, okay, the surfaces in both cases actually behave quite different. Okay. So, okay, so this is the traditional ballistic deposition model, and the version of the model that I'm going to be interested in is the heavy tail version, which is exactly the same as the one I just described. The only difference that now the blocks will have unit width, but a random height, okay? And the heights of all these blocks are going to be IID with common distribution function, which I'm going to call F, that I'm going to assume for the rest of the stock that satisfies two assumptions, okay? First of all, it's continuous, so there are no atoms in the distribution of these random heights. And most importantly, I'm going to assume that the right tail of this distribution, so the left tail is 0 because F is the distribution function of a non-negative random variable, so the left tail doesn't matter. But the right tail is going to be regularly varying with some index alpha in between 0 and 2, okay? So that means that if you consider the tail of this distribution, it's just going to behave like t to the minus alpha times some slowly varying function L, okay? Okay, great. Yeah, okay, so, and the problem that I want to understand, or that we're going to study, is to try and see what's the rate of growth of the surface or the cluster of blocks in this heavy-tailed setting, okay? So it's known that for standard ballistic deposition, the height of the cluster, so if you want like this line, which is kind of an interface, well, grows linearly with time. Okay, but in this case, since I have random heights and these heights are heavy-tailed, you can pretty much see from the picture that these heavy tails account for, or are going to produce some blocks which are extremely tall, some very large heights. And these extremely tall blocks may produce some faster growth of the interface, okay, or of the surface. So I want to try and understand that, okay? If it grows linearly, if it doesn't, what's the speed of growth and whatever. Okay, so yeah. Okay, so the main results that we have are the following. So let h of x, t, and p denote the height at time t of the column of blocks which is sitting above x, okay? So for example, let me go back because I want this to be clear. So in this case, for example, the height would be 4, right? 1, 2, 3, and 4. Okay, even if it's sticking to a neighboring column, doesn't matter. Okay. So the height of this column above x at time t for the model with p sticking. Okay, so the coin is heads with probability p and tails with probability 1 minus p. And furthermore, assume that at time 0, I don't have any blocks. Okay, I just have the real line essentially, well, flat initial condition. So the first theorem says that there exists a slowly varying function L, which is going to depend on the distribution function of these heights. It's not the same L as before, it's related, but it's not the same one as before, such that for any P positive and any X, okay, in the integers, the height above X at time T, when I normalize it like this, okay, so this is basically P to the T squared to the 1 over alpha times a slowly varying correction, so a small correction. This converges in distribution as t goes to infinity to some limit h. This limit h satisfies two things. First thing is that it doesn't depend on p, on the sticking parameter, okay? So basically, all the dependence on p of the model gets washed away in this scaling right here. And the second thing is that this h is actually something that we can characterize. Okay, it's characterized by a specific variational formula, and it corresponds to a last passage percolation problem, something that looks like a last passage percolation problem. But I will talk about that in the next slide. Okay, after the main results. Yeah. Okay. Okay. So that's theorem A, and basically what this tells you is that that for all p positive, the height grows essentially at the same speed, okay, modulo some constant factor which might depend on p, but the speed with respect to t is the same for all values of p positive. And in particular, it's super linear, right? Because t to the 2 over alpha is much bigger than t because alpha is less than 2. But the behavior of the model is actually quite different for p equals 0. Because in this case, since I have no sticking to nearby columns, neighboring columns, the behavior of each column is going to be independent, okay, like what you see here. And actually, you can check that the height above, the height of each of these columns is going to evolve in time according to a compound Poisson process with jump distribution given by this f, okay? And this is because, okay, you can see here in the picture that every time a block falls on one of the columns, in the case of standard 1 by 1 blocks, you need to add 1 to the height. But in the case we have blocks with random heights, what we need to add every time a block falls is the height of the block, which is falling. And that has this distribution f, okay? So this is how you get the compound Poisson structure. In particular, it follows from the generalized central limit theorem that if you take the height above x at time t for the non-sticking case, and you scale it appropriately, then it converges to some stable law of index alpha, okay? And I don't want to discuss this, what this stable law is, and I also don't want to discuss much about the scaling. The only thing I care about is telling you that in this case, from this, which is already like pretty well known, you can deduce that the height for the case without sticking is grows much slower than the case with sticking, okay? It doesn't necessarily grow linearly because I have heavy tails, but in every case, it grows slower than this speed, which is the speed at which the surface grows in the case of positive p sticking, okay? Okay, so now I presented the first result, and basically this tells me that for p positive but fixed, I have one kind of behavior, and for p equal to 0, I have a different kind of behavior. And so what I want to do now is actually take p and let it go to 0 and see what I can get, okay? Now I'm gonna have like a competition between two regimes. On the one hand, Since P is positive, I want to behave like this. But on the other hand, since it's going to 0, I want to behave, well, like that, okay, or like this. So what I want to see is, okay, who wins, essentially, and depending on how I take P going to 0. And okay, so our second result is that if you fix some gamma, some parameter gamma in between 0 and 1, and for each positive time, you define a sticking parameter, which is just t to the minus gamma, then the system which fixes an x, an integer site, and checks for every time t, what's the height above x of the column, or the height of the column above x, for the model with sticking parameter t to the minus gamma, okay? So if we consider this system, then this is going to have a phase transition at a critical value of gamma equal to the minimum between 2 minus alpha and 1. And what this means is that for gamma less than this critical value of gamma, which means that P is going to 0 like this, so it's going to 0 but not too fast because gamma is not too large, then I'm going to have the same type of behavior that I had in theorem A. Okay, so the height of the function of the, the height of the column is going to grow at this speed, and I'm going to have the same kind of limit as before. Whereas if I make P go to 0 but faster than this critical speed, let's say, then I have a different kind of behavior. Then the height of the column above each of these sites grows faster than what theorem A predicts, okay? And as a matter of fact, I get a different behavior for the system. It doesn't behave the same way. So I don't get a limit like this, okay? Okay, so those are basically the two results that we have. Do you have any questions you may want to ask? Let me see how much time. Not, okay. So what I want to do next is explain a little bit what this H is, okay? And for that, I need to define a few things. So the first thing I want to define is a set L, okay, of paths. The set of paths defined on the interval 0, 1, which are one Lipschitz. So that means Lipschitz with constant equal to 1, okay? And such that they end at 0, okay? They end at the site 0 of R. Okay, that's my set of paths. And then I want to define a set delta, which is just going to be a triangle in the plane of vertices 0, 1, 0 minus 1, and 1, 0. So basically this triangle that you see right here. And the reason why I want to consider this triangle is because if you graph all the paths on this set, okay, what you will get is always a path that is contained on this triangle. Okay? So basically this triangle is somehow the domain on which the graphs of all these paths live. Okay. And okay, now that I defined this set of paths and I defined my triangle delta, I want to consider, or I want to define two sets of random variables, two sequences of random variables. One is going to be UN and the other one is going to be MN, okay, as follows. So the UN is going to be just an IID sequence of random variables, which are going to be uniformly distributed on the triangle delta, okay, this triangle right here. And then the random variables Mn, I'm going to define as follows. So first, I'm going to take a Poisson process with rate 1, which is independent of this sequence of the UNs. And I'm going to order the points of this Poisson process in increasing fashion. Okay, so x1, x2, x3, and so on. And once I order them, I'm going to define the Mn, okay, as 1 over the nth Poisson point to the power 1 over alpha. Okay, and this gives me a sequence Mn. So you can check actually that this sequence Mn corresponds to the points of a non-homogeneous Poisson process with some intensity, but I don't want to give the intensity because it's not very important. The only thing I want you to remember is that these weights are decreasing because these values, these points are increasing. Okay, so M1 is bigger than M2, bigger than M3, and so on. And they're all positive. Okay. And so I have these UN and these MN, and the idea is that I'm going to think of each MN as a positive weight, okay, which is going to be located at the position UN inside the triangle delta. Okay. Okay, so once I have these two sequences, I'm going to define my limit H basically as the maximum sum of the weights Mn that can be collected by any single path in this set. Okay, so by any single path, which is one Lipschitz and ends at 0. Okay, so you see that this H is somehow the solution to a last passage percolation problem, which is kind of a continuous version of the last passage percolation problem, because we have weights which, instead of being positioned at the different sides of a given lattice, are now located at random inside a triangle. And we have paths which, instead of being increasing, as they usually are in last passage percolation problems, they are one Lipschitz. Okay. So this is basically kind of a continuous version of a last passage percolation problem. And one remark is that one can check that this maximum is always achieved by a unique path in this set, okay? So that there's kind of a unique optimal path realizing this maximum. Okay, so this is our limit H. Let me see how much time I have left. I don't know. Yeah. This. Okay. So the question that you may have, or that one may ask, is, okay, what does last passage percolation have to do with ballistic deposition, right? Because in principle, we're talking about ballistic deposition. So how does this last passage percolation model get into this picture? So to explain that, I'm just going to focus on the case in which all blocks stick to the first point of contact. This is going to make things a bit easier. Not too much, but a bit. And in order to explain the relationship between our original model and the last passage percolation problem, I want to recall the kind of graphical construction I suggested in the beginning. So imagine that for each x in the integers, I'm going to have an independent Poisson process, which I drew here with these dotted lines, okay? And the red crosses in each of these dotted lines are going to be the occurrences of these Poisson in each of these Poisson processes. And the fact that I have a red cross at some point t comma x of the plane is going to represent the fact that above site x, I have a block which is falling down and sticking to the cluster of blocks exactly at time t. Okay. So somehow these red blocks in the Poisson process, sorry, red crosses in the Poisson processes are going to tell me when and where each of these blocks are falling. Okay. So on top of that, in order to construct the process, I need the random heights of each of these blocks. Okay. So I'm going to think that each of these crosses comes with an independent mark or an independent weight, which I'm going to denote by eta t of x. Eta of tx, where tx is just the position of the red cross, which represents the height of the corresponding block, okay? And so it's pretty easy to check that with all this information, with the marked Poisson processes, I can construct my ballistic deposition model for all times. And so to explain more or less what this construction has to do with last passage percolation, I just need one more thing, which is the notion of admissible path. So let's say that a path going from 0t to the integers, a discrete path, but a path nonetheless, is called admissible if it satisfies three conditions. So first, if it's cat-lag, which since it only takes discrete values means that it's piecewise constant. If all its chums are nearest neighbor, okay, so if the path is at some site at a given point in time, then it can only jump to neighboring sites, and no further than that. And if whenever this path jumps, it jumps to a point or to a site, and at a given time, that is such that it lands on a red cross. Okay. So S can only jump to a given site if it lands on a red cross. Okay. So for example, an admissible path would be, I don't know, starting from time equals 0, then I have a cross here so I can jump, then I continue evolving with time, then I have another cross so I can jump, and then I continue with time. I see a cross, but I don't need to jump. I can go straight and I finish here at time t. Okay, so that's an example of an admissible path. Okay, so once I have these admissible paths, the key proposition which relates our model, the ballistic deposition model, to a last passage percolation problem is the following. So for any t and any x in the integers, with probability 1, we have that the height of the column above x at time t is the maximum sum of the weights associated to these red crosses that I can collect by any single admissible path which ends at x. Okay? So basically, what I have here is another kind of last passage percolation problem where the weights are not located in the lattice, but are in fact located at Poisson points, and these increasing paths are replaced by admissible paths, which also depend on the Poisson points. Okay. So basically, to show our results, what we need to do is to show that this sort of discrete optimization problem, when t is very large, converges to the continuous optimization problem, which defines the h. Okay? And so basically, that's the idea. How much time do I have, Daniel? I have like 30 seconds.
So we have like 7 minutes till the next talk. So hopefully.
No, so I'm really over time. Okay, so I just want to. Fine, I can stop here.
You can take a couple of minutes and then we can.
Okay. No, so the only thing I want to say is that for the original last passage percolation model with heavy-tailed weights, the convergence to a continuous problem, which looks a lot like H, has already been done by Hambley and Martin a few years ago. Okay, and so basically what we have is what they have, and so we follow the same kind of approach. But we have a few differences, and the differences is that, or are that, well, first, we don't have a lattice anymore. We have like a sort of Poissonian lattice, so it's more difficult to control somehow because we have a random number of points which are not located homogeneously, so it's more complicated. And also that the notion of increasing paths gets replaced by now admissible paths, which also makes the whole analysis a bit more intricate than in their case. And one more thing is that what they consider is what in our setting would be the p equals 1 case, and what we have to do is actually prove the same kind of result for all values of p and actually make p go to 0. So this is going to make things, again, a bit more difficult. It's going to require some new estimates and some refined computations, but okay.
Excuse me,
basically,
Santi?
this is what we did. Yeah.
Yeah, maybe you must have said this, but I missed it. Where is P in your graphical construction?
No, P is 1 in my graphical construction.
Okay.
So if you want to take another P, what you need to do is add like a second mark to these red crosses. And this red cross is going to be the outcome of the coin, okay? And so the only difference is that with this is the definition of a miscible path, because if you have an abstract P which is not 1, then a path is going to be admissible if it satisfies 1 and 2, and the only difference is that it can jump to a red cross only if this red cross has a coin which is heads. Okay, and that's the only difference. So if this red cross corresponds to a block, which will stick to the first point of contact. Okay, that's the only difference. If you make that difference, then this is the same formula holds for any value of p. Okay, so that's all I wanted to tell you. Thanks for listening.
So let's thank Santiago. And we do have time for a couple of questions. So Jaime.
Santiago, nice talk. You get the one-dimensional distributions. You have an idea of at least correlations in the limit or between two sides or?
So we didn't check, but I mean, if you take the two sides which are like macroscopically away, then what you will get is just like you will get the same kind of thing, but a different optimization problem. So what you have to do is instead of optimize, so I have the picture rotated, so I have to think. Instead of optimizing over paths in one triangle, I have to optimize over pairs of set of paths over two triangles which somehow overlap. This is what you should get, but it's the same kind of limit, so I'm not sure it's telling us much more.
Could you explain where does the Lipschitz condition arise?
Sorry, where does the what?
The Lipschitz condition.
Okay, so basically because what I want is I want paths which grow no faster than at slope 1 in absolute value. Okay. And this comes from here because this admissible paths, one can show that typically, it's kind of complicated to explain, but this, okay. So these admissible paths will have, let's say, a discrete slope, which in the limit, in the scaling limit, will not exceed 1. Okay. So this one Lipschitz condition comes from taking the limit as it goes to infinity of the scaling these admissible paths. Okay.
But at discrete level, they could exceed slope 1, right?
What?
At the discrete level, they could exceed.
Yes, it could. Yes, it can. But when you scale things and let them go to infinity, then they can't. In the limit, they can't. So if you, for example, if you look at the kind of, okay, let's say you suppose you end here at this point and compute which is the furthest point you can get by jumping on these red crosses, but ending here, okay? So you will get a path like this, which can go very far away, but in the scaling limit, it will look like a straight line which has slope equal to 1. Okay, so that gives you somehow the triangle and the one Lipschitz paths. Okay. I think no.
So
Okay.
Santiago,
Yes.
so at the beginning you showed some pictures, and there were like this. There were these trees, no?
These ones?
Yeah. So, do you have any candidate or guessing of what these trees are? I mean, how these trees
Like the geometric structure of these trees?
Yeah.
Oh, I guess okay, I have to think about it, but essentially every time you have okay, so if you're thinking about this tree in particular, I mean, this kind of just behaves like the standard heavy tail ballistic deposition, but it's somehow reset it at this height. So the fact that you have some very large weight somehow or large height makes kind of this separate from like it's a separate process which starts again, more or less. But kind of what's the geometry of this? I don't know. We don't know. We're just starting with the rate of growth.
But Santiago, there are some loops. They're not trees, no?
What do you mean by loops?
Because then you can grow from the left and the right and touch in some point or not. I'm missing something.
Yeah, you can touch.
Right.
Yeah, you can touch. These two can join. Is that what you're asking?
Yeah, yeah.
Yeah, at some point they can join. But okay, what
Yeah,
happens is that.
Yeah, they have a small connection somehow.
Yeah, because of these guys. So as far as the speed goes, well, maybe this is not the question you're interested in, but yeah, what happens with these guys doesn't really matter. But yeah, they can join. The thing is that okay, this is gonna be so further away from this height, and it's gonna take some. I mean yeah.
Okay, if there's some other quick question, maybe we can take it. Otherwise, okay. So I remind you that we have these breakout rooms. So hopefully you're not gonna break out right now, but maybe later if somebody wants to discuss anything. I do have some questions, but I'm gonna ask them later because of time. Well, we can go to these rooms. So if there are no more questions, let's thank Santi again for the very nice talk and very nice pictures.
Not mine, so.
Well, but you're showing them to us, so.
Well, thanks for the invitation again.